Hi, in this video we are going to talk about applications of BST. In particular, applications of self-balancing binary tree. Because a self-balancing binary tree makes a lot more sense compared to normal BSTs. The reasons are simple. Operations like search, insert, delete, floor, ceiling, greater, smaller can be done in log n time. So what are the applications of self-balancing BST or BST? The first application is to maintain sorted stream of data or to maintain a sorted set of data. When you have a stream of data which is coming in and you want to maintain the stream in sorted orders, self-balancing BST is the best option. Because when you insert an item into self-balancing BST, it takes log n time and you can print items in sorted form at any moment by just traversing the self-balancing BST in in-order traversal. Please note that a self-balancing binary tree can also be used to sort an array in log n time. You can simply insert all the items of an array into a self-balancing BST and then simply traverse the self-balancing BST and it will be an log n algorithm. But constants in self-balancing BST based sorting algorithm are higher. That is why it's not preferred as a general purpose sorting algorithm. Also, it requires extra space for storing the array elements into a self-balancing BST. So self-balancing BSTs are not used as a general purpose sorting algorithm, but they are useful when you have a stream of data, when data is coming in and you want the sorted items at every moment. Not only stream of data, when you have a set of data which you want to keep in sorted order and you want your users to delete items also and you still want to keep them sorted, self-balancing BST is the best choice for these scenarios. The next application of self-balancing binary tree is doubly-ended priority queue. We all know single-ended priority queue can be implemented using heap data structure. When we say single-ended, we mean we either want to find out maximum item from the priority queue or want to find out minimum item from the priority queue. If we always want to find out maximum item, we use a max heap. If we always want to find out minimum item, we use a min heap. What if we want to find out both maximum and minimum items randomly in a priority queue? For example, there's a priority queue for a doctor. You want to find out least priority patient and you also want to find out the most priority patient. Probably you want to tell the least priority patient to go when queue is getting bigger and you want to tell the most priority patient to go and attend the doctor. So when you have both priority operations, max and min, self-balancing BST is the best option because it provides maximum element, minimum element both in big O of one time, and you can do insert delete operations also in log n. How can we do maximum and minimum in big O of one time? You can just maintain maximum and minimum with the self-balancing BST. When you insert an item, you can simply compare it with the maximum and you can make sure that you have the appropriate maximum. When you delete an item, you can find maximum after deletion because deletion is anyways log n. You just need to do one more extra work and you can find the maximum in log n time. So maximum and minimum both can be maintained with the self-balancing BST and both can be answered in big O of one time at any moment. So you can have a doubly-ended priority queue which has maximum, minimum both in big O of one, insert, delete and log n. And it is the one advantage is it can also be maintained in sorted order. The third application is to solve problems like these. You have a set of data and in this set you want to find count of smaller elements, count of greater elements. Suppose you are selling items online. At any moment you want to find out how many items sold below this price, right? So you can maintain these items in a self-balancing BST. You can also use self-balancing BST when you have a set of data and you want to perform the operations like finding floor, finding ceiling, finding greater, finding smaller. The problem that we discuss, finding ceiling on the left side. And similar problems can be finding ceiling on the right side. So if you want to find out from the right side, you can traverse from the right side. It's basically a stream of data that you want to maintain. And in this stream, if you want to perform these operations, count smaller, count greater, floor, ceiling, smaller, greater, all these operations can be done in log n time. And with these operations, you have other operations as well. You have search, insert, delete in log n. You have sorted traversal in big O of n. So when you have these operations with search, insert, delete and sorted traversal, you can always use self-balancing BST. One last thing, if you have only search, insert, delete or a subset of search, insert, delete, it is recommended to use hash table over self-balancing BST because hashing has all these three operations in big O of one time. But if you have subset of search, insert, delete and you have one more extra requirement like you want to maintain the data in sorted form, you want to count the smaller greater or you want to find out the floor ceiling, then it's recommended to use self-balancing binary search tree.